Sure, we can start.
Recording ki on hai galo na?
Sunda, have you started the recording?
Yes, we have started recording and okay, so welcome everyone. Tamal, you can share your slides and
Yes.
we'll start. Okay, so welcome everyone to this fifth session of our meeting. And today, Tamal Guha is going to talk about quantum communication, and this is the second part of his talk. So let's start. And also, I will remind you that if you have any question, just unmute yourself and ask the question. And also at the end, we will have discussion, time for discussion. And okay, so let's start. Tamal.
Thank you. So I'll just briefly revisit all the things we have discussed last day. Just a quick summary that we have first shown that in the scenario of classical communication, the MI, the mutual information, is not the last thing. It can be beyond MI kind of communication. So that's why we refer this Frenkel and Weiner result. Then we go to the channel matrix kind of thing. Then we will show that with in principle result that with unbounded SR, you can simulate whatever quantum communication you can do with a d-dimensional quantum system. You can mimic with a d-dimensional classical system if you have unbounded SR. But we have raised some question that SR could be
One thing. Could you make these slides full screen?
Oh,
it is
sorry,
not
sorry.
yet full screen.
Yes. Sorry. Now it's okay, right?
Yes,
Hello?
it's fine.
Yeah. Okay.
Yes, it's fine.
Yeah. So then we argue that shared randomness could be some resource in when a scenario there is no communication or when it is assisted by some communication. Then we move to this channel matrix thing and we say something about this ultra weak measurization, a specific kind of measurization relation. And at that time there is some question that why it is ultra weak. I found some reference in this paper where they have defined this ultra weak thing, and they said that two matrices X and Y, they will be strongly measurized each, means X will strongly measureize Y if there is a doubly stochastic matrix or bistochastic matrix as that dx equal to Y. Then the question comes, what is weak measurization? If instead of D, this is instead of a doubly stochastic or bistochastic matrix, it is a row stochastic matrix, and the same thing holds, then we will say that Y is weakly measurized by X. And obviously, since this measurization condition require one matrix in the before and another matrix after, that's why it is really referred as ultra weak measurization. So it's one step further from the weak measurization, but still doing with the row stochastic matrix. If anyone interested, they can follow this paper in linear algebra applications. Okay. Now, thereafter, the important thing we have said about the physical interpretation of ultra weak measurization. We say about the monotones under this measurization. We say about the non-negative rank. We give a physical intuition of this non-negative rank, and then discuss that why it could be a potential candidate to identify the classical dimension realizing that communication matrix. So up to this, we have discussed last day. So now I am moving to the new part. So the new part is starting with an alternative definition of the non-negative rank of a row stochastic matrix. So,
Yes, Tamal.
yes.
Can you please go to that ultra weak measurization? I'll just add one particular point.
Yeah, sure. Yeah, here. This one
Yes.
or the before?
No, I'm talking about the definition of ultra weak.
Oh, yeah, this one.
Yes. Okay. Now over here, in this particular case, if you take L equal to identity, then it is the usual L equal to identity, then it is the usual matrix measurization. And if you take R to be the identity, then it is the weak measurization. So in matrix measurization, basically we need both the matrices, we should be of square matrices of the same size. And in case of the weak matrix measurization, we need that the column number should be same. So basically in ultra weak measurization, what is happening, it is generalizing this idea of matrix measurization and weak measurization. So you can think of that if they are all of the same size, then if you take R to be equal to identity, then it is the matrix measurization, and L identity, then it is the weak one. So basically this is the generalized version.
Oh,
In this particular
yes.
case, if you think it in this way, then it will be easier for everybody to understand.
Okay. So, but in that paper, what I was citing, they define something called strongly measurization, which requires the matrix to be doubly stochastic, not only the row stochastic matrix. And
Yes,
in weak
that is,
measurization,
yes.
Okay. Right.
Hello, Tamalda.
Uh-huh.
Am I audible?
Yes.
Yeah, Tamalda, I have just a small question. The last day you talked about some monotones, and this ultra-weak measurization forms a pre-order. So my question is, I mean, is it not an, I don't know if the question is already answered, but is it not an interesting question that whether there exists a finite set of monotones that completely characterize this ultra-weak measurization? Meaning, if I have a finite number of monotones, then I can tell whether A can measurize B or B can.
Right. But you cannot completely characterize, right?
No. Yeah, I cannot completely characterize the question with a single monotone. That's for sure. But I'm saying that does there exist a finite number of monotones? Whether I mean such a characterization is possible with some. For example, in case of coherence, I think there exists some. I mean monotones. I mean which is a finite set, but monotones are not continuous, and you can completely characterize the transformations. But in case of entanglement, it's not possible with the continuous monotone. So in this case, I mean, what is the? I mean, is there any answer, or are you thinking?
Yeah, I do not know, but what I know that these quantities could be monotone for this measurization, but I do not know that whether these number of monotones are sufficiently characterize the total measurization thing. Whether these finite number of monotones are sufficient, that I don't know.
Okay. And also, I mean, so also, I mean, whether there exists some finite number of monotones, n monotones, so that is also not known. I mean,
that I don't know, but I don't know whether there is some result about that.
Okay. Thank you, Tamalda.
Okay. So then, so let's come to an alternative definition of non-negative rank, or an equivalent definition. What it says that you have a row stochastic matrix M cross N. The non-negative rank of this matrix is defined as the minimum number K such that A can be written in a form of M cross K into M of the order M cross K and C of the order K cross N. And you find the minimum number of K such that you can decompose A with these two matrices. And the condition to these two matrices is that both of the matrices are actually non-negative. Again, I am saying this is not positive semi-definite matrix. Do not confuse it with the positive semi-definite matrix. Whenever we are saying non-negative matrix, that means all the elements of this matrix are greater or equal to 0. And there is another result by Cohen, again in linear algebra application in 1993, where they have shown that if A is row stochastic, B and C should also have to be row stochastic in this kind of non-negative rank definition. Okay. I just give this definition as a substitutory part. We will need the definition in the later type. Okay, so before that, let us discuss that what is the implication of the non-negative rank of a row stochastic matrix. Suppose M cross N order matrix, it is a channel matrix, obviously row stochastic. The non-negative rank of the matrix is K. What does this mean? It means that A can be decomposed in terms of two row stochastic matrix, L of the order M cross K and R of the order K cross N. Just follows from the definition beforehand. So obviously you can think that this is actually L m cross K with a K order identity with another R K cross N. And what does this mean? This means if the non-negative rank of a channel matrix or a communication matrix is equal to K, then it is always ultra-weakly measurized by the K order identity matrix. So to say in a different way, in the physical perspective or operational perspective, all the communication metrics realized by a classical DIT must be ultra-weakly measurized by IT or the D-dimensional identity. So this is an important result, and when we go to the quantum case, we will see a significant departure from this result. Okay, so next the question comes that, okay, we understand that if we consider the classic.
Tamal, I have a question, like a comment. So it means that any kind of channel matrix can be generated from the identity K matrix. So it means that any kind of classical noise can be generated from perfect classical channel.
Yeah, obviously you have to emphasize on this classical thing. This is important because I have said that then it's obviously true. Then it is true. Yes.
Yeah, for classical channel, it is true that classical noise, any kind of classical channel matrix can be generated starting from this K identity with some raw stochastic.
Exactly. If the non-negative rank of the channel matrix is equal to K.
Right. Okay.
Right. Okay. Now the question comes that what is the minimal communication element, and that is very trivial. That is just the random guess matrix, which requires actually no communication. So all the elements, if it is a m row n column matrix, all the elements are actually 1 by n. So this means that whatever communication they made, the receiver end, they will just output all the possible outcomes with equal probability. And this means if you have any arbitrary A matrix of any arbitrary order, you can do this kind of thing, that the sender, the Alice, she is actually sending the same system every time and actually effectively sending no system. And the receiver end in the Bob side, whatever outcome he got, he just split it on the all possible n position. So this is the random guess matrix, and it is trivial that this matrix you can generate from whatever matrix you have. So this VMN is actually measurized by all possible matrix of any kind of order PQ. Okay. Hello, could you hear me? Hello.
Yes.
Oh, okay. There is an interaction. Just a minute. Yeah. So what we can say that if the Alice and Bob, they are allowed to communicate a D-level classical system, whatever communication matrix they will generate, that will lie between the random matrix, which will denote as Vn, and the identity matrix, D-dimensional identity matrix. Okay. Now we will define something else, which is called positive semi-definite rank of a non-negative matrix. How to define the positive semi-definite rank? It is simple that you have a M cross N matrix. Now you define a collection of M number of matrices which are of order K cross K, square matrices, and N number of orders which are of order K cross K. Again, they are also square matrices. And the condition is that these matrices, all these R matrices and all these C matrices, they are positive semi-definite. You see, here I am saying positive semi-definite, not the non-negative rank. So that means that standard positive semi-definite rank we know, or positive semi-definiteness we know for the matrix thing, that their eigenvalues are greater or equal to 0 or something like that. And the condition is that the ijth element of this matrix can be generated from trace of Ri Cj for all ij. And now you find the minimal K is the order of the square matrix. And that K denotes the positive semi-definite rank of the matrix A, of the row stochastic matrix A. So rank PSD, we say, rank PSD of A is the minimization over all possible K such that it can be combined with a form of, with a collection of two different collection of positive semi-definite matrices and their traces.
তোমার এই জায়গাটা আরেকবার বলবি এই ব্যাপারটা
Yeah. So what I'm saying that you have some M cross A, M row, N column. You find M number of R matrices. Why M R I am saying it is because just like the row, that's why I'm saying M number of R matrix, all of order K cross K, and N number of column C matrix, all of order K cross K. M denotes the row of the matrix M, matrix A, and N denotes the number of columns for the matrix A. And the condition is that all this R and all this C should be positive semi-definite. And the ijth element of this matrix can be written as trace of Ri into Cj. This is the condition. And you optimize over all possible K and find the minimum K. What is that minimum K? That is called the positive semi-definite rank of the matrix.
Tamal,
Yes.
since minimization is involved in this definition, no? I'm saying let's say R, C, Ri, and Cj all I take one by one matrix is some positive number.
Yes.
One by
But you cannot then manage, right? Because you have a fixed R which has to generate all possible C. You see that for all Ij, Ri, Cj, actually initially when I read this definition, I also tried in this way, that I can choose a particular number, right?
So in in one row I can manage, but then the
Yes, exactly. Other rows you cannot manage. That is the thing.
Fine.
Yes. Yes. Okay.
Great. Fine.
Now, what if? So this is for. So this one is for non-negative matrix. Now, if I consider that A should be a row stochastic matrix, what effectively happen? You can replace this R1 to Rm with some positive semi-definite matrices whose traces are also bounded by 1. Basically, these are the density matrices row 1 to row m. And these are the effects from M1 to Mn. And since it is row stochastic matrix, that's why you can show just by some manipulation that if you sum over all M, whatever you will get, that is identity. So what does this mean? This means instead of these matrices R1 to Rm, you can think that they are quantum states from row 1 to row m. And instead of thinking this C1 to Cn, you can think that that is actually a measurement with n number of outcomes or n number of effects, M1 to Mn, sums up to identity. So that's mean positive semi-definite rank of a matrix gives the quantum dimension, the dimension of the quantum system required, the optimal dimension of the quantum system required to realize the channel matrix A. And this result is actually established in this paper, Mathematical Progress, in 2017. So now we understand, okay, so we define there are many monotones. We write few monotones in the earlier slide. And if we consider particular two monotones under this ultra-weak measurization, one is the positive semi-definite rank and another one is the non-negative rank. The non-negative rank corresponds that the minimal dimension of the classical system you require to realize this channel matrix, and positive semi-definite rank says the minimum dimension of the quantum system you require to reproduce this channel matrix.
Hey,
Now-
Tamal,
Yes.
Tamal, I'm just trying to understand this definition of positive semi-definite rank. That means you are saying that it is the minimum K for which this A becomes a non-negative matrix.
Yes. And this R alpha, no, because R alpha, C alpha, they are also
Positive
positive
semi-definite.
semi-definite. So obviously this will be positive.
No, that is positive. What I'm trying to say that for which this A becomes a non-negative matrix, that means all the elements are non-negative.
Right.
Okay, that means it may happen that I can get a different integer which is higher than this A mean, but I will take the least integer.
Yes. Obviously.
Okay. And in this next slide, like if you want to make it row stochastic, you have taken those RIs to be positive semi-definite matrices with trace 1.
Yeah.
Okay, so like this is just, I was wondering, that means now if suppose I take the measurements also to be probably positive semi-definite matrices of trace 1, then will I get a doubly stochastic matrix? That means I am taking the CIs also to be positive
no, I think then it may happen that the matrix is finally not a row stochastic matrix, right? Because for the row stochastic, the sum of each row should be equal to 1, right? If you do not put some constraint here, if you assume that M can be of trace 1, trace class matrix, then I think this A may not be a row stochastic matrix.
Okay, there will be maybe some problems. Yes. Okay, fine. Okay.
Can I say one thing, Nirmala?
Yeah.
Yeah, I think what you are saying, that will happen if the density operators add up to identity. Means row 1 plus row 2 ... row m add up to identity, then that will happen. It will become bistochastic.
Yes,
but
but
Shahil, in that case, I can take M is exactly identical to row, right? But then it will not be a row stochastic matrix.
Okay. Please carry on.
Okay.
Tamal, hello?
Can I just ask one thing? I'm saying that we know that for any channel matrix, the quantum dimension and classical dimension required are same, right? So actually, are you saying that this positive semi-definite rank and positive rank for all A matrix will be same?
No, that I am not saying. But what I am saying that I am not assuming anywhere in this part of talk that there are some shared randomness.
Because of SR this difference.
SR is not there. Right?
Local randomness. Yes.
Yeah. Okay.
Okay.
Hello, Tamalda.
Yes.
Yeah, so just one question here. That suppose your row 1 to row m, the support of this set of density matrices is not the full Hilbert space. Then you don't need this condition, right? Sum over j mj is equal to identity. You need it to be identity for only that subspace where these density matrices are there. Do you understand what I mean?
Yeah, because you are saying that then these outcomes are actually trivial outcome, right?
No, I'm not saying that. Suppose, yeah.
No,
Those outcomes are trivial outcome.
Yeah. But in that case, you can actually minimizing your dimension, right? Minimizing the k.
No, I'm not minimizing the a.
K. Because
Yes,
you have few feet, but you need only a two-dimensional thing. That's mean I think you can effectively write this k as 2 instead of 3.
Okay, yeah.
I think that is actually.
Okay, yeah. Now I think it is clear.
Okay.
So, Tamal, I just have one more question. Yeah, so like from what you were saying, is this correct? Or if I say that the non-negative rank of a row stochastic matrix basically tells us what is the smallest dimensional classical system required to simulate that A, but without assistance of shared randomness.
Right.
And similarly, PSD rank is the smallest quantum system, but without shared randomness.
Right.
Okay. So that's why these two things can be different.
It can be different in general. Yes, exactly.
Okay.
In
Thanks.
fact, if you go to this next example, what I am trying to show, that you can see that this non-negative rank of this matrix is greater than 2. You have to do some calculation to show this, but you can trivially see that with if you add 2 columns, there is no way to get the third one from there. Or if you want to add 2 rows, you cannot get back the third row with some convex combination or something like that. So this matrix A is not measurized by 2-dimensional identity or 2x2 identity. Therefore, A cannot be realized with a bit of classical communication, that is for sure. But instead of this A, if you consider some peculiar matrices, R equal to like this, C equal to like this, C1, C2, C3, R1, R2, R3, then you will see that all Aij elements are basically trace of RICJ. So that means this matrix A has the positive semi-definite rank to be 2. Therefore, A can be realized with a bit of quantum communication. And now you give the interpretation to these matrices that these matrices as nothing but this R1 is a pure state 0, R2 and R3 are some tilted pure state in the block sphere, and C1, C2, C3 are 3 measurements, basically the prime structure. You can realize that this C1 is basically the 1 projector with some normalization factor 2/3, and C2 and C3 are respectively the orthogonal projector to R2 and R3. So basically, if you want to generate this matrix, what you can send means what Alex can send either R1 or R2 or R3, and Bob in his lab can make a measurement in the basic with the effects 2/3 of C1, 2/3 of C2, and 2/3 of C3, and they will exactly generate this matrix. So there is a counter example where this matrix cannot be generated or cannot be realized with a bit of classical communication, since the positive semi-definite non-negative rank is greater or equal to 2, but can be generated with a quantum communication since the positive semi-definite rank is 2 of dimension 2 obviously. So that's mean if you yeah, so there is a difference we now understand, and we also point out some sharp difference here. Interestingly, not even 2x2 identity is measurized by A. 2x2 identity means, okay, since this matrix has non-negative rank to be greater than 2, it is obvious that this matrix cannot be measurized by 2-dimensional identity. Now, with some calculation, you can show not even that identity, 2-dimensional identity is not also measurized by this matrix A. So, 2-dimensional identity cannot be written in this form. So that's mean a very important and interesting feature. If you consider a D-level classical system, there exists a single class, a unique class of communication matrices with the maximal element to be identity D, means D-dimensional identity, and the minimal element is any arbitrary Vn, the random guessing matrix. And all the communication matrices are ultra-weakly measurized by identity D and ultra-weakly measurizes Vn for D-level classical system. But if you consider the D-level quantum system, there is exactly one known class of communication matrices with the maximal element ID. We call it an equivalent, identity equivalent communication matrix. So if A belongs to this group of communication matrices, obviously it will be between Vn to ID. But this is not the one or the exclusive communication matrix class, because we have seen that this is also a communication matrix which is neither measurizes nor measurized by identity of 2 dimension, but still it is realized by a 2-dimensional quantum theory. So if we ask, so they have in this paper, this Heinossari and Kepro define this in a different way, but I have placed it in a more simpler way. So the problem is that in the classical communication setting, we can define what is the greatest element. that all the greatest element, if you consider the D-level classical system, the greatest element is the D-dimensional identity, because all the communication matrices are ultra-weakly majorized by D-dimensional identity. But if you consider D-level quantum system, we know that there exists one equivalent class where all the communication matrices are ultra-weakly majorized by identity, but there can be possibly infinite such classes, which are completely inequivalent with each other. So in quantum theory, we do not have any greatest communication element till now. And this is obviously an open question, that what could be the greatest communication element in the quantum system, or how many possible equivalent classes a quantum communication could have. Well, so you can go to the detail of this result in this reference, and actually this is actually recently been published in Quantum, which I haven't updated yet. Okay.
Manik, you go first.
So I'm saying this quantum, when I was asking this greatest, for quantum thing, will this set, first question is, will this set be a closed set topologically?
I think at least for this one, it is obviously closed, right? Because we know these elements perfectly.
No, but okay. This maximal, whether it is the least upper bound, that is the question, no?
Oh, you are saying the total set, total communication.
Yes, total communication.
Yeah. We do not have any idea about that.
It could happen.
They have left it open.
It could happen that even the set remains topologically not closed.
Yeah, it may happen, because
still the maximum question remains the
greatest element. Greatest element. It remains again open.
There is a high chance it might become a non-closed set topology.
Yeah. Even possibly there are infinitely many equivalent classes. I do not know.
Yes. And in this example, how beautifully you have put, isn't it very obvious that, okay, to simulate this without any SR, to simulate this correlation, so channel matrix, classically I have to send a three-dimensional system.
Yes.
But quantum mechanically a two-dimensional system can do it.
Right.
But and this gap can be made arbitrarily large if I just now make a 4x4 matrix, all the elements are zero diagonal. Off diagonal, suitably I put the non-zero value looking into the elimination.
Yes. Exactly.
And it can arbitrarily that gap can be made.
Yes, that is the result I was trying to say in the next slide. This is a result.
I see.
Yeah, this is by result by this Heinossari, Plavala, and Oskari Kerpo is there, and another guy. They have a recent result.
That is in a sense very
Manik,
yeah.
Manik, I'm saying it can't be made arbitrarily, no? Till 4x4 you can go.
No. I am not talking about all should be equal. It is not 1/3. Some positive number, I will put it suitably.
Yeah, exactly. Yes.
But then that requires some proof, like.
That proof this Heinossari group they have done.
That is also
very. It can be made arbitrarily large.
Yeah, you can make it even arbitrarily large with any amount of SR. Means if you have a threshold amount of SR and the threshold amount of communication, I can always give a task which you cannot do with this resource.
Exactly.
But with 1 qubit you can do.
But 1 qubit you can do.
I see.
Yeah, I think there is some another question by Shom, I think.
Yeah. So, Tamal, so my question is that can we say that the stochastic matrix, the row stochastics matrices that is measurized by identity and measurizes therein, the set of row stochastic matrices, and that is for the classically, like in the first definition, and the quantum mechanically for the second definition, are these two the same or different? Do they make some? Do Heinossari and
Obviously, these two sets are same. If you consider
two
the
sets are
identity,
same.
yes, because this has complete upper bound, right? ID in the upper side and VN in the lower side. And since the same upper bound is upper and lower bound also holds true for true here, these two sets are exactly same. But we do
But the
not know
other, yeah,
other
that was
set
my.
in quantum case.
Okay. So there
That
exist other. So we
there
can say that
obviously
like.
exists because you can see that this matrix is not neither majorized or nor majorizes I2.
So this we can say that this is like the quantum set here is like classically simulable using a D level, like simulable by a D level classical system. Like we can say that.
Means you, if you are saying about this particular class, this is true.
Yes.
But there could be some, there actually has some class, what we have shown in an example, which is not simulable by a two-dimensional classical system, but can be simulable by a two-dimensional quantum system.
But and that is all also like measurized by identity and measurizes.
Yes. If you consider about this class, this is true, that these two are exactly same.
Thanks.
Yeah, Tamal, can I ask one question? So the thing is that means the crux of the statement is that in case of the D-level quantum system, there is no greatest element, number one.
No.
Yes. And number two, the thing is that if there is a communication matrix which is measurized by identity, that is classically simulable.
Yes, exactly.
If it falls in any other orbit means any other class, then it is not classically simulable.
Right.
Okay.
Yeah, and for your first comment, I should add one thing that we shouldn't say that there is no greatest element, but we do not know the greatest element. There might be.
Okay. Now we do not know of it.
Yeah. That
Okay.
only thing we can say. Yeah.
Okay.
But Tamalda, can you just go back? So you just said no, if you fix some classical bits and some amount of shared randomness, then a qubit can do something that this resource cannot. Right. So doesn't that imply that there shouldn't be any greatest element? Like you can make that element as big as you want, right?
But how do you guarantee that that particular matrix cannot be measurized by some other matrix? Means because you are saying that in qubit I can have any arbitrary n cross n matrix, and neither one of them could be measurized by other. That I think we cannot say, because if you have I'm just saying, I do not know, I have to think about it. If you have a 10 cross 10 matrix in qubit, and if you have a 5 cross 5 matrix in qubit, how can we first say that E05 is not measurized by E5?
I see.
Oh, yeah.
I understood. Yeah, I understand what you're saying. It might happen that A10 measurizes. Yeah, I understand.
Yeah, but obviously there, I understand your point that how can I end this thing? That at which end I can say that, well, this is the last thing. This is the greatest element. That question, I think, yes, that is maybe a good point. Yes, that may happen. That's just due to this, actually, there is this no greatest element is there. It may happen, right?
Okay.
Okay. So this part is resolved by Heinossari, Plawala, and some other collaborators there. So what they have shown, the qubit over d-dimensional classical system, even with SR. How to do that, or how to show that? You have a collection of rows, R matrices. You remember these R matrices, R1 ... Rn, and C matrices from C1 ... Cn. And you can see that since this Ri is chosen just as a vector form, if you sum over all Ci, you will get exactly identity. So this C basically a measurement and R basically a preparation. And you can see that this matrix AN, the ijth element of this AN, is actually of this form. This is a peculiar form. I am not going to this detail. And you can show that this A is exactly a row stochastic matrix. Now you see all these are is actually qubits, and all this C actually qubit POVM element. So finally, we can say that this AN for any possible n, the PSD, this positive semi-definite rank of this matrix is 2. And that's mean with a qubit, you can actually simulate this matrix, whatever n you can choose. Actually, you are choosing this state with same interval, and you can make it infinite in principle. Finitely many or something. Okay. So since AN is a row stochastic matrix, and we see that the positive semi-definite rank of this matrix AN is basically 2. Now, there is another result by Giles and Glenoir in Linear Algebra Application 2012, where they have shown if you have this kind of a matrix, this particular kind of a matrix with this kind of a element and all are diagonal, as also pointed out by Manita, these matrices has the non-negative rank is exactly greater than equal to log n with base 2, and for all n. This positive non-negative rank of this matrix is always greater or equal to log n. Now you consider a situation if you have d-dimensional classical communication with k-dimensional SR. What does this mean? Your effective communication matrix is basically summation over pk and ck. Ck are the individual d-dimensional communication matrix, and pk is the probability of your shared random variable. So whenever you observe a value k star, Bob also observe a value k star, Alice observe k star, Bob observe k star, they will communicate in such a way the ck star matrix, the communication matrix, is realized by the d-dimensional classical system. That's the whole thing. Now, since every ck you are allowed to communicate a d-dimensional classical system, these ck are ultra-weakly measurized by id, because we are talking about classical system. So you can write this ck as lk identity rk, which is basically lk rk of the order m cross d and d cross n. I am assured with this d because this is a classical stochastic, the non-negative rank of the matrix is d, and it is ultra-weakly measurized by d-dimensional identity. So now, all your LK and RK, they are of order m cross d and d cross n. So effectively, you can write C effective, which is of dimension of or order m cross dk and dk cross n. Why this is so? Because each ck of order m cross dk, and you have k number of these ck matrices, so the effective number of columns becomes dk. So this will become a m cross dk order matrix, and this is a dk cross n order matrix, the effective C matrix. Whatever you can do with a d-dimensional classical communication and k-dimensional shared randomness. So, if you now recall the equivalent definition of non-negative rank, we can safely say the effective classical communication matrix, C effective, can be realized, the positive semi-definite, the non-negative rank of this effective communication matrix is strictly lesser equal to dk. Because if you place m cross dk and dk cross n row stochastic matrices, you can exactly generate the C effective. Therefore, the non-negative rank of the C effective is lesser equal to dk. So this effective realization of a dk dimensional classical communication. If you have a d-dimensional classical communication and a-dimensional shared randomness, what the best you can do, the effective realization of a dk dimensional classical communication. So now you consider, you remember this AN matrix. for which the non-negative rank is greater than log n. If I choose this an, n equal to n is greater than 2 to the power dk, then non-negative rank of an is greater than dk. So obviously, if you have d-dimensional classical communication with a k-dimensional shared randomness, I can always choose an n which is greater than 2 to the power dk, which you cannot be simulate with d-dimensional classical communication and k-dimensional shared randomness. But what we have said earlier, that all these an matrices has positive semi-definite rank, so you can mimic it with a qubit. So for every n greater than 2k, we have a an, a communication matrix, which is simulable by a single qubit, but not with a d-dimensional classical communication along with a k-dimensional shared randomness. So whatever d and k you fix, I can always give you a channel matrix or a communication matrix, what you cannot simulate with that resource, but with a two-dimensional quantum communication, even without any SR, you can simulate this matrix. So in this sense, qubit over cdit persists even with SR. So they sell their results. So they said their result in this way, that the in-principle result of Frenkel Weiner doesn't hold in all practical purpose. Because in practical purpose, you will have some limited number of classical communication dimension and the limited number of shared randomness dimension. Whenever you have this thing, you can always define a task what is not simulable by this resource, classical resource, but you can exactly simulate this whole thing with a two-dimensional quantum communication. So this is the main result I was trying to talk about this 2024 very recent result with Heinossari and Plavala and others. Yes.
But Tamal, I have a question. So
Yeah.
doesn't it mean that there is some discontinuity? Because once you make the SR infinite, so let's say, so then to simulate that, you need actually the d-dimensional quantum system. So since now you are only talking about cdit and k-dimensional shared randomness versus a qubit.
Right. Exactly.
So once you make the shared randomness infinite, then the qubit is no longer sufficient.
Exactly.
You have to go to qubit.
Right. If you want to generate all possible
it is not. Yeah, it is a sudden jump. I mean,
yes, it is.
I don't know
there.
how to explain this. I mean, this is very strange.
Yeah, because whenever there kind of a discontinuity comes, because maybe the source of the discontinuity is that this quantum matrices has no greatest element, or we do not know any greatest element for the quantum communication matrix. Because I think these two are actually
the existence of that is sufficient maybe to explain this, but not necessary. I mean, there might be more fundamental.
I'm not saying this, but yeah, I think there is a one-sided discontinuity in this thing, that if you make this shared randomness to be infinite, you will get a matrix for which you require exactly d-dimensional classical quantum system. But if you make a very less, you can simulate by a quantum system. But I think, Shomda, there is one important point regarding this discontinuity. I am not saying that you have a d-dimensional classical communication and k-dimensional shared randomness, whether all possible channel matrices are simulable by a qubit. That I am not saying. I am saying there is an example. So it may happen if you have very large, but
okay. Now I get it.
And if you want to simulate all possible quantum matrices, yes,
of course. You are not considering all possible classical.
Yeah, I am just giving an example.
And k-dimensional. Yes.
Right.
I mean, that might, some other thing might need like higher dimensional quantum systems, maybe.
Yes.
Even for finite case.
At least we definitely know there is one matrix that is identity of d order for which d-dimensional quantum system is necessary.
Right. So, Okay.
So this was the results, the last update by Heinossari and Plavala and his collaborator to attack the in principle result of Frenkel Weiner, which doesn't hold in practical purpose. Now I'll just quickly go through one of our recent results, which will be somehow connected with these results. Now, the obvious question one may ask, well, whatever you are saying, they are actually the perfect qubit communication. If you consider the noisy qubit communication, can we replace a noisy qubit channel in principle? I am saying in principle, this is important. I am not saying all practical purpose. I am going to the Frenkel Weiner status that you may have unbounded SR. In principle result, that can we replace a noisy qubit channel in principle with a noisy bit channel of same capacity? This question actually asked in one of our recent paper, and we are able to show that this doesn't hold true. Means if you want to make a Frenkel Weiner like extension for the noisy qubit communication, this doesn't hold true. What we have shown, we have considered a game where there are 4 boxes and another box contains $1. The dealer who serves the position of the bomb and the position of the price to Alice, but Bob knows nothing about the positions. Alice has to communicate something to Bob such that Bob can avoid the bomb perfectly and get the prize. And we are considering the worst case success probability, that the minimization over all possible combination with a given strategy, what is the probability of getting the prize, and the worst case situation, even of maximizing over all possible combination, the bomb should not be exploded. Means Bob should not open the box containing the bomb. And there we have shown that whatever classical strategy they consider, even with unbounded amount of SR, if the bit channel has capacity strictly less than 1, there is always a finite chance to open the bomb. Actually, one can quantify this amount of amount of explosion of the bomb. So noisy C-bit channel cannot help to avoid the bomb. And then we have shown even there, if there is no SR, then with a classical 2-dimensional system or classical 3-dimensional system, you can perfectly avoid the bomb, but you cannot get any prize. Then we consider something called NOT channel, which is you can just simply see that this is basically an entanglement breaking channel, and this is the only class of qubit entanglement breaking channel for which only class of means up to unitary. This is the class of unitary entanglement breaking channel, only class of entanglement breaking channel for which the entanglement assisted capacity and the classical capacity is exactly same, and that is 1 bit. This is a result by Shirokov in 2012. And then we consider something called Q0 channel, where you, instead of a single measure and prepare channel, you have at least 2 different bases of measurement and some preparation channel. So this is an entanglement breaking channel, and for which the entanglement assisted classical capacity is strictly less than 1. We say it quantum knot because it involves 2 different kind of measurements at least, so kind of incompatible measurements. Well, so what we have shown, that is a big thing. I am not going to say all these things. What we have then go the worst case of this quantum channel, where you are making the measurement in all possible bases and preparing the orthogonal states for all bases. So this channel, interestingly, realizes the universal knot or approximately universal knot gate, which is again an entanglement breaking channel. And what we have shown, that if you see this thing, that if you have not quantum channel, Q0 quantum channel, and U0 channel, U0 is the universal knot, what we have said, approximately universal knot. The entanglement assisted capacity of this channel is 1 bit, this one is less than 1 bit, and this one is minimum over all possible Q0 channel. This is exactly 0.42 bits, some numerical value. And interestingly, if you consider the bomb and prize game, here you can avoid the bomb, but you will have no prize. Here you can avoid the bomb, but you will get a price which is between 0 to 1/3 probability. 1/3 is the optimal one. And if you have the U0 channel, which has the least entanglement assisted capacity, which is strictly less than 1, you will have exactly 1/3 the maximum amount of price obtaining probability with quantum protocol. So what does this mean? You see that this channel, this particular U0 channel has capacity 0.42 bit. Now, if I give you a C-bit channel of capacity 0.42, even with unbounded SR, you cannot do this task. You have a finite probability to open the bomb, and the game cannot be won. So what it in essence saying that if you move to the noisy qubit case, the in principle result of Frenkel Weiner, what it is saying that in principle you can replace a qubit with a C-bit with infinite SR, that also doesn't hold true, because there could have a task where a noisy qubit can do the task perfectly, but a noisy C-bit of same capacity with unbounded SR cannot do the task. But yes, there is one point I should mention, otherwise it is not justified. Our protocol of doing this kind of thing is require a pre-shared entanglement between Alice and Bob, and whenever Alice is sending the qubit through this entanglement breaking channel, that is actually the part of the entanglement she shares with Bob. That is true. Otherwise, this game is not possible. But still, the result in principle holds, because the entanglement assisted classical capacity of all these channels are strictly less than 1. So this kind of result is actually holds. Yeah. So there are some other thing we have done with this paper, but I am not going to all these details. Yeah. So up to this, I think this is the good place to stop. Yeah. Any other question? So yeah, one question what I am also trying to answer these days, that you see that our results, mean the last result what we have said, that the noisy qubit communication cannot be replaced with a noisy C-bit communication, even infinite SR. That proof somehow requires, somehow used the entanglement, the pre-shared entanglement, and we know that even for the entanglement breaking channel, entanglement can increase the capacity. Though the entanglement as assisted capacity of these channels are strictly less than 1, but we know that there are some results that entanglement breaking channel with assistance of entanglement, the classical capacity could increase. So one at this point, a very critical reader or very critical reviewer can argue that, well, this is in fact true, the result in fact true, because you are saying that this noisy qubit cannot be replaced by the noisy C-bit and your entanglement assisted capacity is strictly less than 1. But one critical reviewer or one critical reader can say that no, you have somehow assumed entanglement. So one open question, what I am also trying to answer these days, that whether without using entanglement, it is possible to show that if I have a noisy qubit channel, I cannot replace it with a noisy C-bit channel, even with unbounded SR. And to me, one possible direction, what actually I was trying to work on this direction, is basically there is a result by Christopher Fuchs where they have shown that you could have some classical some quantum channel for which a strange thing actually happens. They are considering exactly mutual information thing kind of communication scenario where you are trying to send some information, I have to decode the information. Our general intuition always says that the orthogonal, whatever may be the noise, the orthogonal encoding in the sender side will be the best to do this kind of thing. But Christopher Fuchs has a beautiful result. He gave an example of a quantum channel, a noisy quantum channel, qubit channel, for which the orthogonal encoding is less powerful than the non-orthogonal encoding. So this can be a potential direction to hint that whether even without entanglement, we can show that noisy qubit communication is powerful than noisy C-bit communication, but with infinite SR. Because if you try to realize the Fuchs results, you require a genuine non-orthogonality in the Alice's side. So that's why I am trying to think that whether that could be a possible direction. Yeah, that's all. And obviously, we have discussed some of the open directions about this quantum communication and classical communication without SR, how to characterize the greatest element, whether there are some greatest element, whether this set is actually infinite or something like that. Yes. Yeah, that's all.
Okay, thank you, Tamal. I will first ask the one question, then I will move on to the other questions. So my question is that in your result, so if you let the entanglement also assist the classical communication, what happens?
For the noisy classical communication, I haven't we haven't proved it formally, but we are more or less sure. We are sure that if you replace it with a noisy classical channel of capacity less than 1, it is not possible. But if you replace
even with assistance of shared entanglement,
yes, it is not possible. But if you have a perfect classical bit channel, obviously this comparison is somehow tricky because your channel capacity is strictly less than 1. But still, if you replace it with a 1 bit of perfect communication, then entanglement can do the same task.
Right. Okay. So are there any other questions? Okay, yes. You can just unmute yourself. Okay, so one by one. Bhivash first and then Monica. Yes, Bhivash. No. Okay, so I guess Monica. The question.
Yeah, Tamal.
Yes.
This last point, this total group result which you are mentioning, it has shown
Right.
that okay.
Sorry,
Clearly here also.
So if we have some quantum channel, and we know that okay, in product encoding, entanglement, decoding in multiple means parallel use of this channel, the final thing is the accessible information.
Right.
And he has shown that, for this his peculiar channel, this non-orthogonal state maximize the capacity means soluble power.
Yeah.
But now we try to think from this HSW theorem, although Schumacher was that such a code exists that is in asymptotically, no? But you are considering single shot.
Right.
You hint I get, but how that result is only saying that non-orthogonality is very peculiar.
Right.
How, because that code will realize in asymptotic sense in parallel use of the channel.
Right. Yes.
Here you are studying single shot.
Yes, obviously.
That's why
No.
it's tricky.
No. I'm not sure whether it will work, but I am saying that maybe this kind of channel could have some importance.
Yeah, this is the intuition that I got.
Yes. That only because you see, for the encoding of this channel, you need somehow non-orthogonality is powerful.
Yes, that is
which you cannot push by classical theory, right?
Actually, that is a good direction because this channel is actually a non-unital. For unital, you will not get all.
Yes, exactly. True.
So another minor point is 2012 result what Heinossari they have used, no? That log n bound.
Yes.
And they have considered a very particular kind of channel.
Yeah.
And that's why the gap is not that much. It is a logarithmic, no?
Yes, yes. But the question is, can we find
Yeah.
something for which the
Yeah,
gap?
but what I'm trying to say, but you see, this construction, full power of qubit we haven't used because we are saying always in the great plane.
Yeah, exactly.
Full power is its 3D power. I was thinking whether something using the full power of qubit, whether the gap can be in principle be stronger than logarithm.
Yes.
Yeah.
We are also thinking in something in this direction.
I see.
Okay.
And probably if you go to seed treat instead of bit to treat, here even a stronger gap might be possible due to non-contextual.
Right.
Qubit three-dimension is there, but in a sense it is dull. Some shy epistemic model is there, contextuality is not there, but Q3 onwards something more powerful thing is there. But the Frenkel Weiner result is for any n level.
Any D dimension, right.
So this
Yes, but
so what shown they are exploring this graph property, graph
Yes.
they are contextually giving the power, whether that kind of things can be in a sense utilized.
yes,
Right.
but in this case, I guess because since you have a fixed measurement,
Yes,
contextuality.
but you see, no, Shom, I understand its measurement, but in a tricky way, no. Look into Spekens and Rovi Kunjal, that single non-commutative measurement in actually sense is not required in non-contextuality, but by using the randomness things, we can incorporate it there. It is a tricky
Yes,
way.
yes.
But I have to go through their paper because there is a paper, no, this perimeter group. They said that okay,
Right.
non-commutative measurement is not required for non-contextuality. Actually, there was this randomized kind of things they do, and in a sense incorporate it.
Who was the author in this paper?
I mean,
Spekens, Rovi Kunjal, perimeter group.
Okay.
so the point is that you can think of a POVM, like some POVM, which is randomization of projective measurements or something like that. Then for every such projective measurement, you have to non-contextually assign the values.
Yes.
Maybe
Because
something of that sort.
Because why I am telling that because you see, Tamal, this what is called this Ambianis. Ambianis, this paper. Is
RSC.
called- Not RSC. What is called this is a very long bit string you have to reduce in small string and then send it to what is called what problem is
The parity oblivious.
fingerprinting.
Oh,
Okay. Fingerprinting. Yes.
So in fingerprinting, actually, Ambien is actually showing fingerprinting kind of task using P-shared randomness is actually gives the exponential advantage. Here you are seeing it in a different way. That, okay, your quantum can be give exponential advantage over the classical resource.
Right.
Because here is the advantage, but it is logarithmic advantage.
But
It is not even linear.
Yeah, it's true, but you see, one important point is there. Here you can put any arbitrary dimension of the classical communication, right? This is another power.
No,
Yes.
and also the classic and the quantum is fixed.
The quantum
Order
is
of n,
fixed.
1.
So if you put D to be again 2, then maybe this K also increase in a high order, right?
Understand.
Yeah.
But yeah, I understand. I understand. Because
But you are asking that, okay, together with D and K, can we give more than or steeper than log n advantage?
exactly.
Yeah.
Because power of quantum is not used because the construction is only great circle of a cube.
Right.
Which is very dull, but still the potential, it is showing the potential. So quantum has too much enormous power. Even qubit, the three-dimensionality, and Q3 towards the context, all these peculiar behavior is sitting.
Right.
I mean, that is just a guess. I
Yeah,
don't know how to come up with it. Otherwise, a very nice talk, Tamal. I've learned lots of things.
Okay, are there any other questions? Okay, if not, then I will stop the recording.
Okay.
Thank you. Yeah. Yes, yes.
Can I just suggest one thing, that since this is a very good direction Kamal has discussed, so I can ask what is called Pratik. Pratik, are you there? Pratik, are you there? Because there is some concept called environment assisted
Yeah.
capacity of
Pratik is not here.
If that can be discussed with continuation of that, that will be very relevant, and this is also new to us also.
No, I do not understand. What are you saying? It's environment assisted classical communication and
Environment assisted classical communication capacity of a quantum channel. These
yes.
are since you have this channel matrix communication theory, this basic build-up you have given, no. So now continuation, that talk will be very suitable here.
Okay.
Sure. We will try.
Yeah.
Okay. So I'm finally stopping the recording.
Okay.
Okay. So thank you everyone.
ठीक है चलो
Yeah.